Welcome to Brain Vision.
Let's start by considering just warming the aluminum ring, essentially making its diameter equal to that of the brass rod, which is 5.05 centimeters. So first we can look in our book and find the average linear expansion coefficient for aluminum, which is equal to 24 times 10 to the negative 6 inverse degrees Celsius. And we also can find the desired change in diameter we want, which we know is just the diameter of the brass rod minus the diameter of the aluminum ring, which is equal to about 0.05 centimeters, or 5 times 10 to the negative 4 meters. Okay, so now let's use the equation delta D is equal to alpha di delta T and solve for delta T to find TF, essentially the temperature needed to expand the aluminum ring this much. We can plug in our numbers. 5 times 10 to the negative 4 is equal to 24 times 10 to the negative 6. The initial for the aluminum ring, which is just 5 centimeters or 0.05 meters, just writing meters to make it extra clear, and then delta T. Solve this for delta T and find that it is 417 degrees Celsius. It could also be Kelvin, but because the difference doesn't really matter which one. But this change of temperature is equal to a final temperature, TF, minus our initial temperature, which you know is just 20.0 degrees Celsius. So therefore, final temperature for this expansion is equal to 437 degrees Celsius. Okay. Now, what if the ring and rod expand at the same time? First thing we want to do is we're going to need to find, once again, the average linear expansion coefficient, but this time for the brass rod. I'm going to write that as alpha b to make it extra clear. And if you look that up in your book, you should find that it is equal to 19 times 10 to the negative 6 inverse degrees Celsius. Now we also need two expansion equations, one for the ring and one for the rod. So for the ring, well, we don't need to write delta D. We can do a D final minus D initial. For the ring, we'll have D1 final minus D1 initial is equal to alpha D1 initial delta T. Likewise for the rod, we'll have D2 final minus D2 initial is equal to alpha D2 initial delta T. We can plug in some numbers, and we can also say that D1 final is equal to D2 final, and just rewrite those as D. Now we know they're equal because in the question we want the ring to just barely fit over the rod. So again, they'll have the same diameter in the end. So let's put in some numbers, simplify these equations. So for the ring, we'll get D minus D initial 0.05 meters is equal to alpha for the aluminum, which is 24 times 10 to the negative 6 times the initial 0.05 delta T. And for the rod, we'll have again D minus 0.0505 meters is equal to 19 times 10 to the negative 6 times 0.0505 delta T. We can move over the negative 0.05 and negative 0.0505 to each other's side, and then write two equal equations for D, the diameter. So the diameter, let's just start with the ring, is equal to 24 times 10 to the negative 6 times 0.05 delta t plus 0.05. Now we also know that that same distance, or excuse me, diameter, is equal to 19 times 10 to the negative 6 times 0.0505 times delta t, and then plus that 0.0505. And again, that's just me making two equal expressions for the diameter d, and then I just kind of set them equal to each other there. Now, if you solve for delta t, you should find that it's equal to 2079 degrees Celsius, which again, like before, we know that's just the final temperature minus the initial, which is 20.0 degrees Celsius. Then we can say, finally, that our end temperature must be 2099 degrees Celsius. Now, in part C, it asks us if this is possible. If you look in the table in your book, you should find that actually aluminum would have definitely melted by this point. It's too hot, so definitely look that up to make sure.